Welcome back. So in this video we'll be discussing the properties of Fourier transform. We'll start with the first one, linearity property. It's exactly the same one as we had in the Fourier series, except that the fundamental difference, Fourier series it was for periodic signals. So वहाँ पे if xt and yt they were two signals, we assume that they are periodic and have the same period t. But here we're discussing the Fourier transform, so there is no concept of periodicity whatsoever. So we have a signal x of t, it has a Fourier transform x of omega. We have a signal y of t, it has a Fourier transform y omega. Then if you form a linear combination of these two signals, like this, then the Fourier transform will be the linear combination of their individual transforms. Right? Then we take the time shifting, that what happens if I time shift a signal, what happens to its Fourier transform. Again, it's quite similar, except that fundamental difference that periodicity exists. Here we don't want the signals to be periodic. So if x of t has a Fourier signal of x of omega, then if you time shift it by some unit, it will be this exponential factor multiplied by the Fourier transform of the origin x of t. You can simply prove it. It's a kind of a similar proof that we did there. So let me just quickly go through it. So x of omega, it will be in terms of an equation, in terms of an expression, minus infinity to plus infinity x of t e raised power minus j omega t d of t. Then if I define a new signal, say let's say y of t is equivalent to this, then transform y of omega, it will be minus infinity to plus infinity y of t, which is this, the shifted version, t minus t naught e raised power minus j omega t dt. Then you can use a series of substitutions. So if I put t minus t naught equivalent to tau, then dt is equivalent to d tau, and as t tends to minus infinity, tau will also tend to minus infinity. If t tends to plus infinity, tau will also tend to plus infinity. Right? So using these, we can have that y of omega is equivalent to minus infinity to plus infinity x of tau e raised power minus j omega. T will be equivalent to tau plus t naught, then d of tau. Then you can just expand the exponential, so it will be x of tau e raised power minus j omega tau into e raised power minus j omega t naught d tau. We'll take this outside, so it will be e raised power minus j omega t naught integral minus infinity to plus infinity x of tau e raised power minus j omega tau d of tau, and this thing is equivalent to x of omega. So this is equal to e raised power minus j omega t naught into x of omega. We had the same thing in the Fourier series. Right? So a signal which is shifted in time, and again then you can take the magnitude and you'll see it will be the same. Fine. So if you take magnitude, because iska magnitude, it will be equivalent to unity. The same thing it also appears here, that magnitude of y of omega, it will be the same as this. It can have a similar kind of generalization, that shifting in time domain does not alter the magnitude of the Fourier transform. Right? Then we had what we had also time. Let's take time scaling first. We'll take the basic operations first. Fine. So this property, that if I have a signal x of t and it has a Fourier transform of x of omega, then if I have a time scaled version x at, apply the Fourier transform, we need to find this. Now just a quick recap. When we did Fourier series, as far as time shifting and time reversal was concerned, they didn't alter the period of your signal. What I'm trying to say is x of t had the same time period as x of t minus t naught. Yeah, x of t had the same time period as x of minus t. But there was a change in the Fourier series coefficient. Right? But as far as time scaling was concerned, it altered the time period of your signal. Right? But it didn't change the coefficient. Right? Now let's try to find out what happens in the Fourier transform. Right? So again, we can do a bit of mathematical analysis. X of a of t, a is a scaling factor, it's a real positive constant. So if I try to find out the Fourier transform of, so if I try to find the Fourier transform of this x of at, it will be minus infinity to plus infinity, the signal x of at, then the exponential factor which is a part of the transform, like this. Right? And again, you can do some substitutions. So if I assume that tau is equal to a of t, then d tau is equal to a into dt, or I can say d of t, dt is equal to 1 upon a d tau, right? And as far as limits are concerned, so it will be same. So if, okay, let me put, if t tends to minus infinity, tau also tends to minus infinity, and if t tends to infinity, tau also tends to infinity. So with all the substitution, let's see what our integral looks like. It will be minus infinity to plus infinity, x of at, it will be x of tau, then e raised power minus j omega t will be equivalent to tau by a, and for dt will have 1 upon a d tau. Fine. So it will be 1 upon a, we'll take it outside. Integral will be minus infinity to plus infinity, x of tau e raised power minus j omega tau by a d of tau. Fine. Now if you compare the basic integral, so x of omega, it would have been minus infinity to plus infinity, x of t e raised power minus j omega t d of t. If you compare this with this, first thing is obvious, you have the factor 1 upon a. Then this is basically the transform of omega by a, because of this tau यहाँ पे भी, tau यहाँ पे भी, so it will be something like this, and this is the transform of x omega by a, which means that if you time scale it, the Fourier transform will be, you'll be first dividing the magnitude by 1 by a, then it will be x omega by a. Okay, so आप कह सकते हैं कि if you take the Fourier transform of a signal that has been time scaled, that scaling factor will affect the amplitude as well as the frequency of your transform signal x of t. Okay? Now this is quite different than what we observed in Fourier series, and the reason is there is no concept of periodicity in Fourier transform. Fourier series में, because your scaling factor xa, it affected the time period, it actually slashed down the time period by the scaling factor, and as a result coefficients were not altered. But here we don't have the concept of periodicity, we don't have any time period. So whenever you time scale, its effect will be that the Fourier transform, the amplitude of the Fourier transform, it will be scaled by the same amount as well as the frequency. Now from here we can have the time scaling, this, what was the other one, time reversal property also. Now from time scaling we know that if I have x of t, it transforms to x of omega under Fourier transform. Then if I scale it x a t, it will be 1 upon a x of omega by a. Now if I choose a is equal to -1, so we have a typical case of what you call time reversal. So if a is equal to -1, it will be x of minus t. It will transform to, since magnitude is involved, so it is like this, to x of minus omega. Now this is similar what we had for time reversal in Fourier series, जहाँ पे हमने देखा था कि coefficients get time reversed. So यहाँ पे जो आपका frequency है, your frequency axis will also be reversed. So x of minus t will Fourier transform to x of minus omega. Okay? So these were the three properties. We have some additional properties, like we would like to know, we had done what you call that basic operation. It was a convolution. Let's see what happens to convolution. So this will be our fourth property. So we have the convolution property. Convolution is a very strong operation. In fact, we used convolution to define our LTI systems, and this was based on impulse response. So we define convolution like this, that y of t is x of t convolved with h of t, and it is basically this integral minus infinity to plus infinity x of tau h of t minus tau d tau, where tau is the dummy variable, right? Now if I take the Fourier transform of y of t, so it will be minus infinity to plus infinity. Then for y of t, I will have, okay, let me just first put it like this, h of t, since y of t is the convolution of x of t and h of t, then we will have this factor which is the part of the Fourier transform, right? It will be minus infinity to plus infinity. This in itself is this integral. So if I substitute it, let me put a bracket, then minus infinity to plus infinity x of tau h of t minus tau d of tau, then e raised power minus j omega t d of t. Fine. So we have two integrals here. If I slightly rearrange them, so let me do like this, minus infinity to plus infinity. Let's take x of tau outside, and let's have in the internal integral minus infinity to plus infinity h of t minus tau e raised power minus j omega t dt. Then what is left is, just a second, what is left is, yeah, okay, d tau, we have d tau here, right? Now we had, if you remember, we had let me just use a second one. We have just done the time shifting property. So if I apply this time shifting property here, so in other words, if the Fourier transform of h of t, it is equivalent to, say, h of omega, then h of t minus what is here, tau, because of the time shifting property, it will be equivalent to e raised power minus j omega tau h of omega. Fine, we just did it. So if I use this kind of a substitution here, let's see what happens. So it will be minus infinity to plus infinity x of tau, and this is basically the Fourier transform of h of t minus tau. So it will be equivalent to e raised power minus j omega tau h of omega. Then we have our own d of tau. Now we can take h of omega outside because integral is with respect to d tau. minus infinity to plus infinity, x of tau e raised power minus j omega tau d of tau, and this, the quantity in this integral, it is actually equivalent to x of omega. Okay. Now this is interesting. Now just try to see what we have done here. We had a signal y of t which was a convolution of h of t and x of t, and the convolution was defined in time domain like this, x of tau. Like I said, it is a complex operation. You have to, we did this, we had first time reverse, then shift, then multiply, then integrate. So it's a combination of 4 or 5 basic operations. Now if I do the transform thing, then Fourier transform of your output, that's y of omega, it will be multiplication of the Fourier transform of your impulse response and the input signal. Now this is interesting. If you remember, I told you that you may ask that why do we go for transforms? So I told you that many a times your transform, it simplifies your operation. Here I gave that example of power spectrum analysis, that you are interested in finding the power content of different frequency components in your signal. Now this is a typical example. In time domain, you have the convolution operation, which is defined by this integral. But in frequency domain, this convolution operation turns out to be a multiplication operation. Right? So you can say that Fourier transform, it actually maps the convolution of two signals into the product of their Fourier transforms. Okay? Now h of omega here is the Fourier transform of the impulse response. We sometimes call it a frequency response of the system. And it plays, we will see that when we do the analysis of LTI systems, it plays an important role. Because in time domain, आपका LTI system was defined by h of t, the impulse response. So correspondingly in frequency domain, it will be defined by h of omega. We sometimes call it system response, frequency response, there are different names. But the bottom line here is that we have proven here that many a times doing a transform, using a transform, it helps to simplify your operation. Like in this typical case, convolution operation was converted to a simple multiplication operation. Okay? We will do a couple of more properties. That will be the part of next video.